Hello, everyone, and a warm welcome to the concluding lecture on the module describing intermolecular forces and the physical properties of liquids and solids. What you have learned in the module about gases and in this module should have given you an overview of the properties of the three phases of matter: gas, liquid, and solid. In chemistry, when we refer to a phase, we usually mean a homogeneous part of a system that is separated from the rest of the system by a well-defined boundary. For example, when an ice piece floats in a water, the liquid water is one phase, and the solid water, the ice piece, is another. Although the chemical properties of water are the same in both phases, the physical properties of a solid are different from those of a liquid. When a substance goes from one phase to another, we say that it has undergone a phase change, and this is going to be our main topic in this lecture. So, phase changes in a system are generally caused by the addition or removal of energy, usually in the form of heat. Familiar examples of phase changes are summarized in this figure. Please note that the establishment of an equilibrium vapor pressure is involved in two of these phase changes: vaporization and condensation. In the lecture on the properties of liquids, we learned that the vapor pressure of a liquid increases with increasing temperature. In fact, when the vapor pressure reaches the external pressure, the liquid boils. Thus, the boiling point of a substance is defined as the temperature at which its vapor pressure equals the external atmospheric pressure. As a result, the boiling point of a substance varies with external pressure. For example, at the top of a mountain, where the atmospheric pressure is lower than at sea level, the vapor pressure of water, or any liquid, reaches the external pressure at a lower temperature. To reformulate, the boiling point is lower in higher altitudes than it would be at sea level. The temperature at which the vapor pressure of a liquid is equal to 1 atmosphere is called the normal boiling point. Since the boiling point is defined in terms of the vapor pressure of the liquid, it is related to the molar heat of vaporization, the amount of heat required to vaporize a mole of substance at its boiling point. Indeed, the data provided in this table show that the boiling point generally increases as the molar heat of vaporization increases. Ultimately, both the boiling point and the molar heat of vaporization are determined by the strength of intermolecular forces. For example, argon and methane, which have only relatively weak dispersion forces, have low boiling points and small molar heats of vaporization. Diethyl ether has a dipole moment, and the dipole-dipole forces account for its moderately high boiling point and molar heat of vaporization. Both ethanol and water have strong hydrogen bonding, which accounts for their high boiling points and large values of the molar heat of vaporization. Strong metallic bonding causes mercury to have the highest boiling point and molar heat of vaporization among the liquids presented here. Interestingly, benzene, although nonpolar, has a high polarizability due to the distribution of its electrons in delocalized pi molecular orbitals. The resulting dispersion forces can be as strong as, or even stronger than, dipole-dipole forces and hydrogen bonds. The opposite of vaporization is condensation. In principle, a gas can be liquefied either by cooling or by applying pressure. For instance, cooling a sample of gas decreases the kinetic energy of its molecules, eventually causing the molecules to aggregate and form small drops of liquid. On the other hand, applying pressure to the gas by compression reduces the distance between molecules, allowing them to be pulled together by intermolecular attractions. In fact, many liquefaction processes use a combination of reduced temperature and increased pressure. You should also know that every substance has a critical temperature above which its gas phase cannot be liquefied, no matter how great the applied pressure. Critical pressure is the minimum pressure that must be applied to liquefy a substance at its critical temperature. At temperatures above the critical temperature, there is no fundamental distinction between a liquid and a gas. We simply have a fluid. A fluid at a temperature and pressure that exceed the critical temperature and critical pressure, respectively, is called a supercritical fluid. Supercritical fluids have some remarkable properties and are used as solvents in a wide variety of industrial applications. The first large-scale industrial use of a supercritical fluid was the decaffeination of coffee with supercritical carbon dioxide. The following table lists the critical temperatures and critical pressures of a number of common substances. Here again, the critical temperature of a substance reflects the strength of its intermolecular forces. Benzene, ethanol, mercury, and water, which have strong intermolecular forces, also have high critical temperatures compared with the other substances listed in the table. Now, let's move on to solid-liquid phase transitions. The transformation of a liquid to a solid is called freezing, and the reverse process is called melting or fusion. The melting point of a solid, or the freezing point of a liquid, is the temperature at which solid and liquid phases coexist in equilibrium. The normal melting point of a substance is the temperature at which it melts at 1 atmosphere, and perhaps the most familiar liquid-solid equilibrium is that of water and ice. At 0 degrees Celsius and 1 atmosphere, this dynamic equilibrium is represented by one of these two equations. A glass of ice water at 0 degrees provides a practical illustration of this dynamic equilibrium. As the ice cubes melt to form water, some of the water between the ice cubes may freeze, joining the cubes together. Remember that in a dynamic equilibrium, forward and reverse processes occur at the same rate. Since molecules are more strongly held in the solid phase than in the liquid phase, heat is required to melt a solid into a liquid. Here, you can see the heating curve for the conversion of gaseous water to ice and vice versa. It shows that when a solid is heated, its temperature increases gradually until it reaches the point at which the solid begins to melt. During the melting period, we see the first flat portion in the heating curve, where heat is being absorbed by the system, yet its temperature remains constant. The heat helps the molecules overcome the attractive forces in the solid, and once the sample has melted completely, the heat absorbed increases the average kinetic energy of the liquid molecules, causing the liquid temperature to rise. The subsequent vaporization process can be explained similarly. Here, the temperature remains constant during the period when the increased kinetic energy is used to overcome the cohesive forces in the liquid. Finally, when all molecules are in the gas phase, the temperature rises again. We should also briefly discuss the molar heat of fusion, which is the energy required to melt 1 mole of a solid. The following figure lists the molar heats of fusion for the substances you saw earlier, along with their heats of vaporization indicated in orange. If you compare the columns in blue and orange, you will see that the molar heats of fusion are smaller than the heats of vaporization for each substance. This is consistent with the fact that molecules in a liquid are still fairly closely packed together, so some energy is needed to bring about the rearrangement from solid to liquid. On the other hand, when a liquid is vaporized, its molecules become completely separated from one another, so considerably more energy is required to overcome the intermolecular attractive forces. Cooling a substance has the opposite effect of heating it. So, if we remove heat from a gas sample at a steady rate, its temperature decreases. As the liquid is being formed, heat is given off by the system because its potential energy is decreasing. For this reason, the temperature of the system remains constant over the condensation period. After all the vapor has condensed, the temperature of the liquid begins to drop again. Finally, continued cooling of the liquid leads to freezing. At this point, I should introduce you to a related phenomenon called supercooling. Supercooling is a phenomenon in which a liquid can be temporarily cooled below its freezing point. Supercooling occurs when heat is removed from a liquid so rapidly that the molecules literally have no time to assume the ordered structure of a solid. As a result, a supercooled liquid has many similarities with supersaturated solutions and is unstable. Gentle stirring or the addition of a small seed crystal of the same substance will cause it to solidify quickly. The final phase transition we should cover is the solid-vapor phase transition. Solids can be vaporized, so they also have a vapor pressure. Sublimation is the process by which molecules go directly from the solid phase to the vapor phase. The reverse process, in which molecules go directly from the vapor phase to the solid phase, is called deposition. For instance, naphthalene, the substance used to make mothballs, has a fairly high vapor pressure for a solid. Thus, its pungent vapor quickly permeates an enclosed space. Iodine also sublimes. At room temperature, the violet color of iodine vapor is easily visible in a closed container, especially when heat is applied. These vapors condense around the container as beautiful purple crystals, just like what you see in this demonstration experiment. Since molecules are more tightly held in a solid, the vapor pressure of a solid is generally much lower than that of the corresponding liquid. The vapor pressure of a solid can be estimated by the molar enthalpy of sublimation of a substance, which is the energy required to sublime 1 mole of a solid. In fact, the molar enthalpy of sublimation is equal to the sum of the molar enthalpies of fusion and vaporization. The equation you see here is, in fact, another illustration of Hess's law, as the enthalpy or heat change for the overall process is the same whether the substance changes directly from the solid to the vapor phase or if it changes from the solid to the liquid and then to the vapor phase. The overall relationships among the solid, liquid, and vapor phases are best represented in a single graph known as a phase diagram, which summarizes the conditions at which a substance exists as a solid, liquid, or gas. In conclusion, we should briefly discuss the phase diagrams of water and carbon dioxide. This figure shows the phase diagram of water. The graph is divided into 3 regions, each of which represents a pure phase. The line separating any 2 regions indicates conditions under which these 2 phases can exist in equilibrium. For example, the curve between the liquid and vapor phases shows the variation of vapor pressure with temperature. The other 2 curves similarly indicate conditions for equilibrium between ice and liquid water and between ice and water vapor. Also, note that the solid-liquid boundary line has a negative slope. The point at which all 3 curves meet is called the triple point, which is the only condition under which all 3 phases can be in equilibrium with one another. For water, this point is at 0.01 degrees Celsius and 0.006 atmosphere. Phase diagrams like this enable us to predict changes in the melting point and boiling point of a substance as a result of changes in external pressure. So, the normal melting point and boiling point of water at 1 atmosphere are 0 and 100 degrees Celsius, respectively. Following the phase diagram, we can say that increasing the pressure above 1 atmosphere will raise the boiling point and lower the melting point, and vice versa. A decrease in pressure will lower the boiling point and raise the melting point. The phase diagram of carbon dioxide is generally like that of water, with one important exception: the slope of the curve between solid and liquid is positive. In fact, this holds true for almost all other substances. Water behaves differently because ice is less dense than liquid water. The triple point of carbon dioxide is at 5.2 atmospheres and minus 57 degrees Celsius. Another interesting observation about the phase diagram for carbon dioxide is that the entire liquid phase lies well above atmospheric pressure. Therefore, it is impossible for solid carbon dioxide to melt at 1 atmosphere. Instead, when solid CO2 is heated to minus 78 degrees Celsius at 1 atmosphere, it sublimes. In fact, solid carbon dioxide is called dry ice because it looks like ice and does not melt. Because of this property, dry ice is extremely useful as a refrigerant. To sum it up, in this lecture, you are introduced to the phase changes between solids, liquids, and gases, which include melting or fusion, freezing, vaporization, condensation, sublimation, and deposition. You learned that the boiling point of a substance is the temperature at which its vapor pressure equals the external pressure, and the normal boiling point is the temperature at which its vapor pressure equals 1 atmosphere. We also discussed the definition of critical temperature, which is the temperature above which a gas cannot be liquefied by applying pressure. A related concept is critical pressure, which is the pressure necessary to liquefy a gas at its critical temperature. You were introduced to phase diagrams, which represent the phase of a substance under any combination of temperature and pressure. You observed that a substance above its critical temperature and pressure is a supercritical fluid. In the end, we briefly analyzed the phase diagrams of water and carbon dioxide and discussed the interpretation of data provided by phase diagrams. In the following module, we will discuss the physical properties of solutions. Thank you for your attention and participation.